So if you're struggling with solving static equilibrium questions, I'm going to walk you through an example to show you the exact strategy that you need to use, regardless of the exact situation going on in the problem. These are the steps that are going to get you a solution, kind of like I said, no matter what kind of problem you have, but if it's static equilibrium. So in this question, we have a potted plant that's hanging at the end of a rod. We have the weight of the plant, we have the weight of the rod, and we see that there's this rope here angled at 40 degrees to the horizontal that attaches the end of the rod to the vertical wall. So we're going to calculate the tension in the rope and calculate the X and Y components of the force at the hinge where the rod meets the wall. So I want you to think about this, and if there's anything that you get out of this video, I want it to be this. You need to use a problem-solving strategy. So rather than memorizing all of the steps to this specific problem, there's like 4 steps that you need to know, just like generally, to get through problems like this. So step number 1, after you've like read the problem carefully, you see what quantities are given and what's not, and that kind of thing. The next thing that you want to do with static equilibrium problems is draw a force diagram. So if you have a picture like you do here, you can draw it right on top, or you can draw this out as just a long rectangle. So most objects pretty much, like, unless it's a sphere or a cylinder or something like that, most objects can be modeled as a rectangle. And now we want to think about what forces are acting on that object and draw them where they act in the correct direction. So we notice here we have this potted plant that's all the way on the end, and that's going to pull downward. So we have this force from the plant at the end of the rod. The other thing we want to pay attention to is the fact that the rod itself is given a weight. So the gravitational force on the rod should go on your force diagram. And that we're going to put right in the middle at like the halfway point in the length. In addition to that, we have this angled tension force. And those are the 3 obvious ones, but there's actually 2 more. There's a force from the wall, there's a horizontal component and a vertical component, and we'll just draw those in the component form. So we have a force that is kind of like a normal force, like perpendicular to the wall. I'm going to call that Fx. And we also have an upward component to that force, which I'm going to call Fy. So number 1, we're going to draw this force diagram. Number 2, we're going to choose a pivot point. And something that we want to remember about pivot points is that if there are forces that we don't know, we want to choose a pivot point to be able to eliminate those forces from our net torque equation. And in part A, we're trying to calculate the tension in the rope. So if we are trying to calculate tension, we would not want to choose our pivot point at the end where our tension force is acting. We don't want to pick that one. We also don't want to pick a point like here at the gravitational force because we know what that force is. So we can pick our pivot point here because that X and Y components of those that is unknown. So let's go ahead and choose our pivot point here. And the next thing that we're going to do after we choose our pivot point is write our net force and net torque equations. So we'll start with the net torque equation. So when we're writing the net torque equation, we have to think about the sign of torque. So if it'll cause counterclockwise motion, that's positive. Clockwise would be negative. So our tension force, and the way that I like to think about this, if you have some trouble with this, is if you had this object fixed at the end, and this tension force was like a string that you were going to pull, would that cause clockwise or counterclockwise rotation? So if you were to pull where that tension force is acting, that would cause counterclockwise rotation. So that means our torque from the tension force is positive, but the torque from the gravitational force and the torque from the plant would both be negative because they would both produce a clockwise rotation. So for our net torque equation, so this is static equilibrium, so our net torque is 0. So if our net torque is 0, we want to look at what makes up our net torque and we will write an equation that includes the torque from tension, the torque from the gravitational force, and the torque from the plant. So we have the torque. I'm gonna like really break this down step by step for you guys. So we have the torque from our tension force minus the torque from gravity minus the torque from the plant. We'll set that equal to 0. And again, we're gonna set this up to solve for tension in the rope. So we'll break this down like one more step and then we'll start to rearrange stuff. So if you remember torque, the equation for that, we are multiplying force times R times the sine of the angle between those two things, and R is the distance from the pivot point to where that force is being applied. So our tension, the torque from tension, we're gonna write that as our tension force. And in this case, I don't know if you picked up on this initially, but they don't give us the length of this rod. So we can write R in terms of length. So we know that this tension force is acting all the way on the end. So we're gonna write R as L, or the length of the rod. You'll notice that this cancels out. And then we have the sine of the angle for our tension force. We'll keep that there because this one's not 90. And then we have our gravitational force that acts at the position L/2, because we know that this is, we'll assume this is a uniform rod, so our gravitational force is acting at the halfway point. And then here, our gravitational force is perpendicular to our lever arm, so sine of 90 degrees is 1, so we'll leave that out. And then we have the force from the plant, also acting all the way at the end of the rod, so we'll write R in terms of the L. And again, we're setting that equal to 0. It's also fine if you just leave it as R instead of L, it doesn't really matter. So we'll solve this equation for tension in terms of our variables. So that gives us tension as Fg times L/2 plus the force from the plant times L divided by L times the sine of the angle between the tension force and the lever arm. So notice here, our L's cancel out. So that leaves us now to plug in some numbers here. So we have our 20 Newton force times 1/2 plus the force from the plant, 100 Newtons, divided by the sine of 40 degrees. And that all brings us to a force for that tension of about 171 Newtons. All right, so that's our process for using the net torque equation to calculate one of our unknown quantities here. So we know that our tension force is 171 Newtons. All right, so let's go ahead now and answer part B. So we want to calculate the X and Y components of the force exerted at the hinge where the rod meets the wall. And here's where our net force equations are going to come into account. So if your thought process now is like, okay, should I be going with a net torque equation, but choose a different pivot point? That option, here's why that's not going to help you. If we were to do that, so say for example, if we were to switch our pivot point from the left end to the right end, we would be able to calculate Fy because that would exert a torque, but the angle between Fx and R would be 0. The other problem there is we don't, that would give us essentially like 2 unknowns in that equation. So it kind of doesn't work for multiple reasons, but now we're gonna use a net force equation instead. So if we wanna use a net force equation though, we do have to think about the fact that we have X and Y components of force. It's not really one net force equation, it's actually 2. And so think about here, you have 3 unknowns. You have tension, you have the X component, you have the Y component of this force. So if we have 3 unknowns, we need 3 equations. So here's our other 2. So our net force along the X axis, again, has to be equal to 0, but it comes from this horizontal component of tension and this horizontal component of the force at the wall. So we'll write that as Fx minus tension X equals 0. And then the Y component, net force along the Y axis, this one is a little bit lengthier. We have more stuff here. We have the Y component of the force of the wall and the y component of tension. Those are both positive because they're both pointing upward. And then we'll subtract FG and FP because those are both pointing downward. And we'll solve these two equations for Fx and Fy. So if Fx is equal to our x component of tension, that would be our tension force times the cosine of 40 degrees, or 171 newtons cosine 40. So the x component of our tension force comes out to be about 131 newtons. And then for our y component, we have our Fg, Fp minus our y component of tension, which would be our whole tension times the sine of 40 degrees. So 20 newtons, 100 newtons minus 171 sine 40, and that y component then comes out to be just about 10 newtons. All right, so just to recap a little bit, in this process here, we first, after reading the problem, we created a force diagram, making sure to include all of the forces and not forget about the ones at the wall, which is one that you would commonly forget about. And after we created our force diagram, we chose a pivot point that helped us eliminate unknown or tricky to find forces. After that, we were able to write our net torque equation and solve for one of our unknowns. And then we also used our net force equations in component form to find our other two unknown quantities. So I hope this helped you out. And if you have other problems like this, like static equilibrium problems that you're struggling with, remember to follow through on that process. So draw your force diagram, choose your pivot point, write your net torque and net force equations, and look for unknowns to solve and ways that you may substitute within those equations. All right, so if you are, having trouble with questions like this, you want more problem solving strategies and walkthroughs, make sure that you subscribe and follow along as you prepare for AP Physics 1 or other algebra-based physics tests.